Okay. Okay. Okay, so we're at the final lecture of this series. So as I promised today, we're gonna look at experiments where people are trying to adapt this platform to do applications in quantum information processing. Towards the end, hopefully, we will try to kind of summarize what we learned about this platform and what are the challenges that still remain in applying this particular platform to different applications in quantum science, but also to look at what are the opportunities that we have ahead. Okay, so today we're gonna look into this mode of operation, the digital mode, because this is the one that is more suitable for this quantum information processing idea. So the things that I want to talk about today are the following. So first of all, we need to look at what is the toolbox that we're gonna use. So the different things we need to understand is how we encode qubits using Rydberg atoms. How do we do single qubit operations, 2 qubit and potentially multi-qubit gates? How do we arrange the atoms to have any-to-any connectivity? And how we do mid-circuit operations like mid-circuit readouts that many of you have been asking in the past few days. We are going to look at some applications. So we're going to look at what has been done to do the first steps towards the realization of quantum error correction. And then we want to comment on the different versions of these Rydberg atom arrays that have been studied so far. So we mentioned in the first lecture that you can use alkali atoms, but also alkali and earth atoms or atomic mixtures to do this kind of experiments. So most of the things so I will start by introducing these tools using the alkali atoms, which are the ones that have been explored first and are in a sense a little bit further ahead, even if now it's not super true anymore. But anyways, I will introduce these tools using alkali atoms. Some of them are general for all these different platforms. And then towards the end, I will comment on how these two different types of platforms can introduce different features and different, so these slides were made for this. In particular, these two different platforms have some interesting features that help with more convenient types of qubit encoding and with mid-circuit operations. Okay, so this is the idea. So let me start with introducing all the tools that we need. So first thing is, in the lectures that I've done so far, the qubit that we've been using, so the two levels of our electronic structure that we've been using were the ground state and one specific Rydberg state. And this is what is mainly used when you do quantum simulation experiments. But for the experiments that I'm going to talk about today, we do a change of qubit, and we use instead a so-called hyperfine qubit. So in this case, the qubit is encoded in 2 hyperfine levels of your ground state manifold, and you only excite the Rydberg state momentarily to introduce interactions, but then you always go back to the hyperfine qubit. Why do we do that? This hyperfine qubit has a lot of interesting properties. First off, it has much longer coherence times in the tweezers. So here we can go with T2. Do you guys know what is T2 and T1 in qubits? Okay. There are 2 relevant times that you need to define for qubits. One is called T1, and that is your spin relaxation time, which means I prepare my qubit in 1, how long does it take for it to decay to 0? And T2 instead is the coherence time. So it tells you, you prepare superposition, how long does it take for the phase to decohere? Okay, so T2 is typically the more delicate one. And in this case, using this hyperfine qubit, you can go up to seconds. The longest that has been demonstrated so far is 12 seconds. Okay, so this is the first feature. We want to use this qubit because it can live longer, and so we can do many more operations within its lifetime. The second feature is it's the state manipulation here have much higher fidelities, and also the readout has much higher fidelity. And finally, since the atoms in these two states are non-interacting, they're more suitable for universal quantum gates, meaning it's good to have interaction when you want to have it, but it's also very good to not have it when you want it to be off. Okay, so we can play this trick to use this qubit and only excite to the Rydberg state when you want interactions to occur. Yeah. I'm going to show you in the next slide. Okay, so this is the qubit that we're going to use when we talk about alkali atoms. I'm going to define different types of qubits when we switch to the alkaline earth. Okay, so coming to the question, now how do we do single qubit operations? So this is, for example, the level structure for rubidium-87. All the details here are not relevant, but these are the two states that we use for our qubits, the 0 and 1 state. The separation is about 6-7 gigahertz. So what we use here are, okay, if we want to do imaging, cooling, and all these things that are not super relevant right now, we use this transition to this 5p3½ state. But what is relevant that I want to talk about now is how do we do hyperfine rotations? So how do we do single qubit operations on these hyperfine qubits? You can do two things. So this frequency here is in the microwave region. So you can do microwave pulses that are very reliable and robust, but they're quite slow. They're typically quite slow. The alternative is that you do Raman transitions. So you do a 2-photon transition going off resonant from some other state up there. So this frequency now is in the near infrared regime. So you do this with lasers, and this can be done much faster than with microwaves. Yeah. It's just related to the control and to how much power you can put in there. So what's the Rabi frequency that you can get? And it's typically not that high. Yeah, so this is an example of the Rabi oscillations that you can get when you do it with Raman. I think there's a factor of 10 if you do it with microwave. It's 10 times lower. But so I think this is one of the highest pi pulse fidelities that people have seen using Raman transitions. The state of the heart, the highest ever seen, has been done with microwaves. So even if this is lower, the fidelities are a little bit higher right now. So, but this can probably be improved with some technical upgrades. But anyways, you can see here that the fidelities for these single qubit operations are already quite high. That we're already in the 4/9. So this is a part of the experiment that works pretty well. But now we want to talk about 2-qubit gates. So how do we entangle the atoms? So the native 2-qubit gate that we use in this system is a so-called CZ gate. So this is a controlled phase gate. And so the map that you want to apply is the following. So you want the 3 states that have at least one atom in the 1 state to acquire a -1 phase, whereas the 0,0 stays in its original state. Now this so the protocol to do this CZ gate was originally proposed back in 2000, and it was a clever idea that used Rydberg blockade. The only problem here is that to implement the CZ gate, you will need to have local Rydberg coupling. So to be able to excite selectively either the control or the target atom, which is technically a little bit challenging, as I was mentioning, I don't remember if yesterday or the day before, to have this kind of local control is kind of challenging because you need to be very good at controlling the intensities such that you have exactly the same omega and delta on each atom. And that's not that easy. So the question is, can we realize this kind of gate, this CZ gate, only using global Rydberg coupling? So what I showed you in the past few days that all the atoms are homogeneously coupled to the Rydberg state, which is much easier to do in the experiment. Okay, so this is something that was realized in 2019 with this protocol that we call the Levin-Pickler gate, for the people that invented it. So the idea is the following. Let's say that you have these row of atoms, and you divide them in pairs such that the atoms within the pair are blockaded, but the different pair of atoms are not, okay? So the different pairs of atoms are basically non-interacting. Now here you have both, so all the atoms are have this coupling to the Rydberg states and the one between the two qubit states, 0 and 1. So as we said, this is a target map that we want to implement, and let's see how we do that. Now, when you're in this situation, okay, the 0 state is not coupled to the Rydberg state. It's off resonance. So when you shine the atoms with the Rydberg light, nothing happens to 0. But what happens to 1? If you have an isolated atom, non-interactive with anything else, that atom is coupled to the Rydberg state with Rabi frequency omega and a certain detuning that you fix. But now if you have two atoms in one, and they're both coupled to the Rydberg state, what happens is that if you look at the energy states for the pair, you're gonna be coupled to the entangled state that is the superposition of RG and GR. Does this make sense? So you have two states that you can couple to, and so you have the entangled state, so-called W. And this has an enhanced Rabi frequency that is multiplied by square root of 2, because you're effectively coupled to two states at the same time. So here we have two level systems. One is the 0-1 state that is coupled to 0R, or the 1-0 state that is coupled to R0. And the other one is the 1-1 state coupled to this entangled state W. Okay, so the tricky thing here is that you have two-level systems that have different Rabi frequencies, but you want them to do exactly the same thing. So this is the challenge in this kind of protocol where you have global coupling. Yeah? Sorry, G is the ground state. So it would be 1. It would be 1. Sorry, yeah. So one of the two atoms remains in the initial state and the other one goes to R. Sorry, that comes from different slides. Okay, so this is what we do. We apply a first pulse with our Rydberg light with a certain duration tau and a fixed phase of the laser. And so we now look at what happens on the block spheres that represent the two different two-level systems. So we set the duration of this pulse such that this two-level system completes a full oscillation around, a full trajectory around the block sphere. So if it starts from the South Pole, it will go back to the South Pole. Since this two-level system has a lower Rabi frequency, when you do the same pulse, it will stop somewhere on the block sphere. It won't be able to go back. So what we do next is we change the phase of our laser, and doing that basically rotates the axis for our rotation, for the evolution of our system. And we choose this phase such that when you apply a second pulse with the same duration, if you look at what happens as this two-level system is that it completes the trajectory and ends up in the South Pole again. And this one, since does the same thing that it did before, so it does a full rotation on the block sphere. Now, does this make sense? No, I see one head. No. Sorry? Yeah, so what is the difficult part? Mm-hmm. Okay, so maybe to motivate from the beginning. So what you see here in this map is that we want these two states. This one is basically the same as the 1-0, right? So we want these two states to do exactly the same operation. But the tricky part is that they have different Rabi frequencies. So how do you create a dynamical evolution of the pair such that they undergo the same exact time evolution, okay? So this is a trick. This sequence of pulses is a trick such that you start with the atom in the South Pole of their respective block spheres, and they both go back. So what you need here is to go back exactly to the same states, but to acquire a phase of -1. The phase is going to come in a second. So this first part is what's the trick to have an evolution such that they both go back to the same initial state. The next part is how do I ensure that they have the same phase, -1. So what we implemented so far is this part of the map. Okay, nothing happens to 0, 0 because it's not coupled to the Rydberg state. These 3 states have gone back to their initial state, but they've acquired a phase. In terms, in block spheres language, this phase that they acquire is proportional to the area of the trajectory that they perform on the block sphere. So basically is this area here. I don't have a way of highlighting it. So it's different for the two, but we can have the two. So these two things are equivalent to each other up to a global phase, single qubit phase, if this is true. So if phi 11 is equal to 2 phi 0 minus pi, phi 01 minus pi, sorry. So we need to find a way to make these terms equal to each other. And so if you look at the phase acquired by the state 11 and the phase acquired by the state 01, they are identical for a specific detuning of your Rydberg laser. Again, this I know you're confused. So the idea is the area that is enclosed by this trajectory is dependent on the detuning of your transition, because basically the detuning fixes the orientation of this axis for the rotation. So if you change that axis, you change the phase that is acquired. And so if you tune that, you can find a solution for which these phases are identical to each other. Okay, more or less. Okay, yeah. Yeah, so the difference is that this state here is coupled to two different states. The one where the Rydberg excitation is on the left and the one where the Rydberg excitation is on the right. And so there is an enhancement of the Rabi frequency because of that. Okay. Yeah. Mm-hmm. Yeah, it's an e to the I. So basically it's a period of that. So you need that e to the I phi 11 is equal to e to the phi 10, and so this is satisfied in this situation. Does it sound right? Does it make sense? No. Okay, we can look at the math, but it works out. So basically, you get the same number if you satisfy this. Okay, so this was implemented in this paper that I mentioned before in 2019, and the CZ gate fidelity that was obtained using this type of gate was the highest recorded up to that point, which was 97.4. Okay, so this was tested in this experiment, at this point 4 years ago. But, these 2-qubit gate fidelities are still limited. So if you actually want to do, for example, error correction, this is too low. And so maybe for reference, these are numbers from the Google experiment, the superconducting qubit experiment. And what they reported recently for their CZ gate is a fidelity of 99.4. And this is, I think, is the highest for any platform up to this point. And, so this was our gate back in 2019. And specifically, what is the gate fidelity that we're looking for? What is a minimum that we will be satisfied with? We need to look at what are the thresholds for quantum error correction. I guess after these lectures, you're familiar with this concept, but in error correcting code, you have a threshold, which means when you increase the distance of your code, does the logical qubit error rate increase or decrease with the increase of the distance? And so this defines a threshold for your gate error. For example, for the surface code, which is one of the lowest threshold, it's 1%. Sorry, one of the lowest is 1%. So we want to have gate fidelities between 99 and 99.9%, depending on the kind of error correcting code that you want to implement. There is a range between these two numbers. So getting to this range of gate fidelities is super important to be able to realize a large-scale quantum computer. Okay, so recently there have been significant improvements in the gate fidelities that have come from two different things. The first one is new ideas on the protocol for the entangling gates that I will show you in a second. And the second one is the implementation of technical improvements to reduce the two main sources of error that existed up to this point for this 97.4. Those two sources, I mean, I decided not to go too much in details because, again, most of you are theorists, so maybe you're not super interested, but the two main sources of errors up to this point were the intermediate state scattering, which means we have this two-photon transition to go to the Rydberg state, so we go through an intermediate state, and so there is some scattering that comes of that, and so about 1% of our error here, of our error here was coming from that. So the main source of error was that. And the second one was we had some dephasing due to finite temperature of the atoms. So by reducing the intermediate state scattering and cooling our atoms to lower temperatures, we managed to improve the gate fidelities as well. So, but let me show you what's the different protocol that has been proposed recently. So this was the protocol for the Levin-Pickler gate that I just told you about. Recently, in 2022, there was a proposal on how to do something similar. So again, you have only global coupling to the Rydberg state, but instead of doing the two pulses with the phase shift in between, what you did here was have a single pulse in the amplitude of in omega. And in the meantime, you have this continuous phase change. So this realizes something very similar. But why is it convenient? Because it's much more robust and tunable in experimental conditions. So this is a figure from the experimental paper that I'm going to show you the results of in a second. The idea here is that if you have, for example, some, when you're applying this pulse, for example, let's say, in the experiment, you cannot really do a square pulse. It would take some time to turn on your laser, right? So there is an error in the pulse you're performing. And just by tuning some of the parameters of this pulse, you can find a solution that is optimal again, but it's optimized with the experimental parameters that you have. Does it make sense? And the reason why this is more tunable is that you have this nice continuous change of the phase that has many parameters that you can tune. And so you can see here, for example, this is the calibration that we do in the experiment. You can just look at, you change the amplitude. Maybe the one that the theory would give you is this one, but you see that if you change it a little bit, you get to a higher fidelity, and then you can change the frequency of this modulation, you can change the tuning. So by doing this, you see that you get to very high fidelities that I'm going to show you in a second. Did I see a hand? Yeah. Yeah, so this is what I talked about, I think 2 days ago. So the way we go from the ground state to the Rydberg state is via an intermediate state, and we do a two-photon transition like this. So it's a two-photon transition. When I plot it, I always plot it as if it was just one single optical transition, but in reality, it's two. So the off-resonance scattering comes from this. So what we did recently was the further you detune your transitions from that state, the lower the scattering rate is, and so the smaller is the error. Okay. Okay. Anything else here? Okay. So this was the idea of this new protocol for the gates. And so let me show you the results that are very recent. These are just a couple months ago. Okay, so here in the experiment, what we did to benchmark the fidelity of the new CZ gate, we did two different things. The first one was to prepare a belt state using the CZ gate. And so you see here, you can measure the population in the two states of your belt pair superposition and measure the parity that measures the phase between them. Okay, I won't go too much into the details of how we measured this. I don't know how much you're interested in this, but basically we could benchmark the fidelity of the CZ gate during these measurements of the belt state pair to 99.5. We did a second type of measurement, a different kind of benchmarking protocol, where we apply a sequence of random rotations to our qubits, interspersed with entangling gates. And then at the end, we do a carefully calculated rotation to bring the initial state, to bring the pair back to its initial state. So it would go back to 0, 0, which is the initial state, if no errors occur in between. So the fidelity with which you return tells you something about the fidelity of the CZ gate. And from this different type of benchmarking, we also get 99.5%. And these experiments are performed on 20 to 60 qubits in parallel. So it's not just on a pair of qubits. It's fairly homogeneous on a pretty large number of qubits. Yeah. So the gate we apply, it's a controlled phase gate. Then you can transform it into a CNOT or into other types of 2-qubit gates by applying other single qubit rotation. Oh, to an arbitrary phase? Not really. You should do something different to do that. Yeah. Yeah. So if you only want to do a CZ gate on a specific pair and not on everything. Okay, so this, I will show you some experiments later in which there are some local operations. So as I mentioned, the main difficulty in doing that is to have homogeneous, you don't want to have to calibrate the gate on each different pair. You want to have something that works for everything. So that's the trickiest part. I think the approach that people are mostly thinking about right now is, let's say that you want to apply a 2-qubit gate on this pair here and not on everything else. What you can do is detune out of resonance everything else, and then still apply a global control for the Rydberg, such that only the pairs that are not detuned are gonna do, because this is more robust. Even if the light shifts on the other pairs is not exactly the same, the only important thing is that they're not on resonance, so they're detuned from resonance. So this is, I think, the approach that people are thinking about. You will see very soon that another thing you can do is just move pairs in different regions. So if you so let's say you have all these pairs of atoms. You want to apply a gate to this one and this one. You move them to a so-called entangling region. This is what the team at Harvard is working on. They call it entangling zone. So you move this to here. And this is where you have your Rydberg beam. This, of course, implies that you need to move atoms back and forth when you want to entangle. What they're doing right now is exactly this. So you're going to see a paper fairly soon where they do this. The alternative, as I said, is you shift out of resonance these two, you keep them in place, and then you apply a gate on everything. And only these two will undergo the CZ gate. Does that make sense? Yeah. No, this is a global thing. So this wanted to represent the beam. So the beam covers all the atoms that you put in this zone are gonna be, excited to the Rydberg state. So when you put them in, they're gonna everything that is in this area is coupled to the Rydberg state. Well, the CZ gate implies applying some Rydberg passes, right? So if you're in this zone, you perform a CZ gate. If you're not, you don't. Mm-hmm. Sorry, so the CZ gate happens if your atoms are within a blockade radius of each other. So this one and this one are not interacting. It's two separate pairs. Yeah. Yeah, exactly. And I'm going to show an experiment that does exactly that in a second. Okay. Anything else? Okay. Okay, so here we've gotten to this 99.5 fidelity that, as I said, was in the range that we were aiming for, between 99 and 99.9. But maybe let me comment for a second on what are the remaining errors and if we think we can go higher or there is some fundamental limitation. So this is just to give you an idea of how this 2-qubit fidelity has improved in the past, 15 years. So the first results using this original protocol that I showed you at the beginning with the local control, I think they were about 80%. And so this is the Levine-Pickler gate that I mentioned before in 2019. And this is this recent result that I just showed you a second ago. So things are, improving fairly fast, especially from 2015 to now. There's been quite a lot of work. This is a table. I'm not going to comment on this again. Theorists don't really care about these things. But just to give you an idea, we have a pretty good understanding of what are the error sources. So our simulations of the error gates are in very good agreement with with what we find in the experiment. So this is what you would expect, taking into account these estimated sources of error. And as I said, what we find in the experiment is 99.5. So what we want to get to is more around 99.9, at least the next result. So the first good thing is that we do understand where the errors come from, which is great because at least you can try to address them. And second, we have an idea of how to get to 99.9 by reducing the two strongest sources of errors that are still the ones that I mentioned before. This Rydberg decay is related to this off-resonance scatter. No, sorry, wrong. This Rydberg decay is related to the lifetime of the Rydberg state. So when you're in the Rydberg state, the Rydberg has a final lifetime of like 100 microseconds. And so this gives you an error on the 2-qubit gate. And this T2 star is also related to temperature. Yeah. Mm-hmm. Sorry, I couldn't understand all. Mm-hmm. 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 How much does it matter, like in applications? Well, for example, if you look at error correcting codes, some of them have thresholds that are higher than that. So you need to get to 99.9 to be able to implement them. So for example, for the surface code, this should be already enough. But for other error correcting codes, it's not. So, and maybe just to clarify, it seems like this 0.3, 0.4% is nothing. It's, sometimes it takes more to get from 99.5 to 99.9 than to get from 80 to 99.5. Okay, so there is an idea. So if you increase Rabi frequencies by a certain amount and you increase the detuning of these two photon transition, we expect to see 99.9, at least from simulations, this requires new lasers and stuff like that. But hopefully we will be able to test this fairly soon. Okay. So now I want to mention this thing that we already saw a little bit yesterday, the fact that we can move the atoms in between our quantum operations. So to reiterate what I was just mentioning here, when you have a pair of atoms, that pair will be entangled only if the two atoms are within a Rydberg blockade. So when you have your array of atoms, let's say that this is your array in 2D, only when you apply your Rydberg pulse, only the atoms that are close to each other within a blockade radius are going to be entangled. Does this clarify your point from before? So all of them are coupled to the Rydberg state, but only the ones that are really close to each other within the blockade radius will be entangled. Okay. So one challenge here is that these entangling gates are naturally local. And this is something that is common to many other quantum platforms. You typically use some kind of local interactions to implement these entangling gates. And this is a little bit of a limitation because for many applications, you would like to achieve non-local entanglement, which means that you want atoms on this side of the array to be entangled to atoms on the other side. So one way of doing it is that you just entangle to the next one, and then to the next one, and then to the next one. And so you proceed and you go through the array, but this is very costly because it means that you need to do a lot of gates. An alternative that we recently developed is the following. So you entangle exciting to the Rydberg state, and then you always map down to the hyperfine qubits, as I mentioned before. So here you have your entangled atoms, but in the hyperfine manifold. So here you have long coherence, the atoms are not interacting, and so on. And then, so now you have entangled atoms in the hyperfine manifold. And then you can use your tweezers to move the atoms across the array. So up to this point, we only use the movable tweezers to rearrange the atoms at the beginning of everything, to initialize them in a certain array that we wanted to use. In this case, we move the atoms in between our quantum circuits, right? We do an entangling operation and then we move the atoms. And we can do this in parallel over many atoms at the same time. So you do an entangling gate, you map down to the hyperfine qubit, and then you start moving your atoms. So by doing this, you basically have an array with different connectivity now. The atoms that are close to each other are not the same that were close before. And so when you apply a second Rydberg pulse, now you have a new layer of gates with different connectivity, right? As I just said, the atoms that are now connected are a different set of atoms with respect to what you had before. So now you map down again, and now you have achieved long-range connectivity just by doing this sequence of local gates plus atom transport. Okay, is this clear? Okay, so this was a very interesting new tool that we developed last year. And let me first of all demonstrate that we can do this while maintaining coherence in our atoms, because you could wonder, okay, you entangle your atoms and now you start to move them around, don't you mess up with their quantum states? So the first demonstration is the following that we did. We prepared 2 rows of atoms. We entangle them in pairs, and then we move the 2 atoms in each pair away from each other by about 100 microns. And then we measure the fidelity of the Bell state before and after the movement. Here I'm only showing the measurement of the 2-atom parity, which is one of the 2 measurements that you have to do. But what you see here is that there is really no change. The fidelity is exactly the same. Of course, if you do the transport in the proper way, if you start accelerating your atoms like crazy, you do lose fidelity. But what we saw here is that you can preserve coherence when you transport the atoms over 100 microns, like I'm showing here, over a few hundred of microseconds. So this seems a little bit of a long time, like the typical time of our, for example, to do an entangling gate, we do it in like a half microsecond. So this is much longer. This is hundreds of microseconds. but it's still much shorter than the T2 time that we have for these hyperfine qubits. So you can still do like 10,000 operations before you get to the decoherence time. So this has a lot of applications. I showed you yesterday how we used this exact idea actually in reverse. So we had the two separate pairs and then we put them together to do this interference measurement to measure entanglement entropy. But I'm going to show you now that it has a lot of applications for quantum error correcting. So these are a few of the things that we tried to do to demonstrate this new tool in this experiment again from last year. So you saw yesterday the measurement of entanglement entropy. And then I'm going to show you today some of these other experiments where we prepare some interesting states for quantum computing. I'm not going to show you the STING code, but I'm going to show you the 1D cluster state and the toric code. Okay, so let's start with the cluster state. So here we have a 1D 12-atom cluster state. So this is the circuit that we're trying to implement. So we start with all the atoms in 0. We apply a first pass on each qubit individually. And we do a first layer of gates. So we entangle atoms in pairs like this. But then we want to perform the second one, which has a different connectivity. So what we do is we move the atoms such that we prepare them in these different pairs. And then we apply a second layer of gate. Then we do, again, a single qubit operation on some of them. And this allows us to initialize the atom in this cluster state. And by measuring the stabilizers, we can see that we indeed prepared our array of atoms in the right state. Okay, this is a simple demonstration that shows you how you can use this to change the connectivity, apply different sequences of gates, and prepare an interesting quantum state. Okay, maybe even more interesting is a toric state. The nice thing here is that we can do it on an actual 3D torus. Even if the atoms are in 2D, using this atom movement, you can, even if the atoms are in 2D, you can close the boundary conditions in two directions. So it's effectively a 3D torus. So let's say that these are the qubits of your, the data qubits in your toric code. What we do in this experiment is to add some extra qubits that are our ancilla qubits. And we use this to mediate entanglement between the data qubits. So the data qubits never interact directly, but the entanglement is mediated by the ancilla qubits. And this is how it works. So basically, you want to apply, you apply this sequence of gates where for each cross of data qubits, you have that the ancilla qubit in between moves close to each of the 4 atoms and performs a sequence of 4 entangling gates. And then we have a final rotation of the ancilla qubit to prepare the right types of connection in your toric code. So again, as I said, this is actually in 3D. I mean, this graph is not, it doesn't show all the connections, but you can close along both directions. And so this is a movie that maybe I already showed, but this shows you exactly how we implement the toric code. So here we have the atoms that I marked in black are our data qubits, and the red ones are our ancilla qubits. We first prepare them in these 8 pairs. We perform a first entangling gate, and then we start moving the ancilla atoms around and perform other entangling gates with different pairs of atoms connected to each other. At the end, we move the ancilla qubits away because we want to apply some selective operation only on the ancilla qubits. So we localize a beam only on those atoms. Okay, so this is, you know, I think, I don't know, at least the movie is very cool, but it's an interesting application of how you can use this tool of the atom transport to implement something that is interesting for quantum computing. Just to give you an idea, if you wanted to do the same thing, but only using local gates, the number of gates that you would have to apply to transport entanglement through the whole array would be much, much larger. Yeah. It's still a CZ gate. So these are all controlled phase gates. It's, yeah. Yeah. Yeah, then this is okay. This is it should be. It should be. Yeah, it should be. Yeah. Yeah. At the end. You mean when I move them up? Yeah. It's no. I think we actually do it on purpose because we might be doing something. Now I don't remember exactly what we do there in the end. To measure the state, we do some operations to the qubits in the end. But I don't think so. Well, actually, okay. So sorry, wrong answer. The right answer is when they're close, when they're moving in general, they're always in the ground state. So when we move them up, they're not interacting. So basically here, when you see them moving, they're always in the hyperfine states. When they get close together, then we transfer them to the Rydberg state, and then we go back. So when they're moving and when they're moving up, they're not interacting. Yeah. No. I'm gonna talk extensively about Midcircuit readouts in the next few slides, so I'm gonna get there. Actually, I'm gonna get there in 2 slides, I think. That's exactly the next step. You know, how do you actually do error correction, being able to apply feedback and so on. It's the next step to this. I saw, yeah.
Sorry, so you're saying that the flow gets put in the river state to this entanglement state, right?
Yeah, yeah.
I thought sort of they go off the graph once they hit the river state.
So here, okay, this is a good point. So here, what we do is, as I mentioned yesterday for the quantum simulation experiment. So when you excite to the Rydberg state, you turn off the tweezers temporarily. But this is, again, this is like a fraction of a microsecond. So it's a very short time. Then before moving, of course, you turn on the tweezers again. And then you excite to the Rydberg state, then you excite back, you turn on the tweezers, so all the atoms are trapped again in this case. Either, you know, being them in 0 or 1, they all get trapped, then you move them. Yeah, that's a good point. Thank you for asking. Yeah. So when I move them up here, it's because I want to apply this operation only on the ancilla qubits. And so I move them away so that I can apply a pulse only on those atoms. And then when I measure everything. You see this final measurement happens on everything because the way we do imaging right now in this experiment is that we image all the atoms at the same time. So here we're only initializing the toric code. We're not doing any error correction. Actually, we're just initializing the toric code. So in the next slide, I can show you, we take these measurements in the end and we measure the stub. Does this answer your question? I see yours still.
But you only get
you only get the toric code after you do this single qubit operation. Well, yeah, but then when you measure them, you measure everything, right? So you measure the ancilla qubit and the data qubits. Okay. Well, okay, you can consider this part and this part like a separate thing. So the measurement on the ancilla qubit creates the toric code, and then you measure the data qubits to check that you have prepared the right thing. Okay, yes, it's a good point. Sorry? Yes, you're correct. Yeah, so we do something like that. So we look at the measurement of the ancilla qubit to do kind of a there is kind of a feed forward just in the readout, just in the post processing of the data. Yeah, exactly. Okay, so just to show you, then we measure the stabilizers. So these are the expectation values for the stabilizers on the X plaquettes and the Z stars. And we can measure the expectation values of the logical operators. maybe something is interesting here is that being this on a torus, you actually have two logical qubits because you have the two directions. And so here I'm plotting both the raw expectation values and the error detected one. So what you can do here is, so what we're doing here is very silly. So we're just post-selecting on the repetitions where we saw that all the stabilizers at the right expectation value. So when those are 1, then we post-select very close to 1 for the expectation values of the logical operators. Okay, so this is the first demonstration. Of course, this is just the initialization of the toric code. We're not doing any actual error correction, but I think this demonstrates at least that this atom transport and the fact that we have this highly parallel optical control allows us to do some efficient realization of quantum error correction. But then going back to the question from before, of course, if we want to do to actually do some error correction, we want to be able to do Midcircuit readout. So in this type of experiment that I just showed you with the alkali atoms, a kind of easy way of doing Midcircuit readout is, as I showed you before, we can move the ancilla atoms and the data qubits away from each other. And so then we can localize an imaging beam only on one of the two groups of atoms. And so, for example, here, if we move the ancilla atoms up here, we can only image this with a resonant beam and leave these atoms alone and unperturbed. So this is work in progress in the Harvard group. They've done it, so you're going to see a paper soon. There is a different approach that doesn't separate spatially the two groups of atoms, but actually tries to shelve some of the atoms in a different atomic state such that they're not sensitive to the imaging light. So there is this other approach that was on the archive a few months ago that you can look up. But now let me get to, so do you have questions? Yeah. You do. Yeah, and I'm gonna show you a first attempt to do that in a recent experiment. Yeah, for now, I mean, so for now, this type of imaging is still destructive, not just in the sense that you perturb the quantum state, but also that you really lose the atoms or you heat them up. In any case, you need either to replenish or to cool them down. There are ways of doing readout that are non-destructive. They're not as efficient, so they take more time. The fidelities are not as high. So there might be something happening there, but for now, the approach is we need to get more atoms back and just replenish the ancilla atoms that we've lost. But I'm going to show you that there is an early demonstration of this. So I want to show you a few recent results that have been done, but that have been implemented with alkaline earth atoms and atomic mixtures, because these two different kinds of experiments actually add some new tools to this toolbox that I just talked about, where you can see how there are some features that are really convenient and that you can use. Okay, sorry, this is wrong. Okay, so these alkaline earth-like atoms are a new research direction with tweezers that had been started by 3 groups, Manuel Andres at Caltech, Jeff Thompson at Princeton, and Alan Kaufman here at GILA around 2017. And the idea here is that when you use these slightly more complex atoms, these alkaline earth-like atoms, they have 2 valence electrons, and so they have a more interesting spectral structure. And these are the interesting features. This is a slide that I stole from Adam, who's in the audience. Thank you. Okay, so the interesting features are the following. So here we're considering the electronic structures. You have a 1s0 state in the ground state. So this is very stable. It has very long coherence times. You can, so you have a 3p0 state that you can that you couple to with this clock transition. You can use another fairly narrow transition to cool, exciting to the 3p1 state. You have another transition here that you can use for detection and also cooling. And then finally, you can couple this 3p0 state that is a metastable state, so you can use it as a qubit state as well to any Rydberg state that you want to use. The interesting thing here is if you take fermions, they have a nuclear spin. For example, for ytterbium, you can have 1/2 and 5/2. For strontium, you can have 9/2. And the experiments that I'm going to show you now are all related to ytterbium with the 1/2 nuclear spin. And so you can use this nuclear spin as your qubit to encode your qubit. And now this is a very interesting qubit encoding, because when you have j equals 0, the nuclear spin degree of freedom doesn't really couple with electronic degrees of freedom. And so this is very convenient, as I will comment in a second. It basically isolates your nuclear spin from many different sources of noises that affect the electronic states. Okay, so this field of what has been done with alkaline earth atoms recently is kind of crazy. So the papers that I'm going to show you are all from the last couple of months. So I did my best to put this together. They're not the best slides that you've seen in these days, but I just want to give you a quick idea of what are the tools that you can use here. So this is an idea that was originally proposed for ion qubits, but has been recently translated into atomic qubits by the group of Adam here at Giulia. So what you use here is the fact that you have 3 different types of qubits that you can use. One is the optical qubit. So as I showed you before, you can couple your ground state to these 3p0 states. So this was your metastable state here, where you have the clock transition. Then you have a nuclear spin qubit, both in the ground state and in the metastable state. So you have 2 different types of nuclear spin qubits that you can use for your quantum operation. And again, as we mentioned before, the degrees of freedom, the electronic degrees of freedom and the nuclear degrees of freedom are well separated if you have j equals 0. And so you can really consider these as 2 different sets of qubits that don't really interact with each other. The interesting thing is that you can use this structure to, on one side, perform Midcircuit operations, as I will show in a second, and also perform erasure conversion, which is another experiment that I will talk about. Also, as I was saying, these nuclear spin qubits are very interesting for 2 main reasons. The first one is that they're very robust to light shifts. I didn't mention this much before, but one of the main limitations of these hyperfine qubits that you have in alkali atoms is that if you have differential light, so if you have inhomogeneous or time-dependent light shifts on your atoms, meaning the tweezer that you use to trap your atoms is fluctuating in intensity, or you have the different atoms of slightly different trap depth, that causes a huge differential light shift between your the 2 states of your qubit. And this causes noise and so limits the coherence. That's one of the main sources of the coherence. In this case, since you have this separation between these 2, you're very robust to light shift. You're basically insensitive to this kind of noise. And the second feature is that these nuclear qubits can have a very long T1 time. So this relaxation time that I was talking about before. Okay, so sorry, this is a super busy slide. This is a picture from Adam's recent paper. So what they did, so the first application that I want to show you about this interesting electronic structure is how you can use it to do Midcircuit operations. So again, here we're using these 3 types of qubits: the optical qubit, the metastable state qubit, and the ground state qubit. You can control each of these, again, using optical transitions. So this is the first type of demonstrations that they did. So here, for example, you have 2 rows of atoms, and you assign the first row as your ancilla qubits, and the second row as your data qubits. Okay, so what you do here is you have some local light shift. So maybe going back to some of the questions before, what you can do, you see this 532 nanometer light is localized on some of the atoms, specifically on all the ancilla qubits. What you can do is you apply a light shift with these local beams to detune these ancilla qubits from a certain transition. And then what you do is you transfer the data qubits to the metastable state. So you do this operation. You initially had your qubits in the ground state. You transfer them to the metastable state, but only the data qubits will do this because the ancilla qubits are detuned away from the transition. Is this part clear? Okay. So now you have the ancilla qubits in the ground state, the data qubits in the metastable state, and then you can map back. So for example, here you can take an image after you do this shoving operation. You see you only image the ancilla qubits because the data qubits are not visible right now because they're in the metastable state, so they're not resonant with the imaging light. Then you can map that back and you take a second image and you see that they're all back where they were. You can also see that you can preserve the coherence of your data qubits if you originally prepare them in some superposition. So doing this shoving operation doesn't really affect the coherence of your atoms. So this is a first demonstration, going back to the question before, this is a first demonstration of how you can do mid-circuit readout if you can shove your atoms to another state that is not resonant with your imaging light. And so it's not affected when you do a pulse of your imaging light. Okay, so again, busy slide, but the idea here is that you can apply this to do different kinds of mid-circuit operation. So I just showed you that they did this mid-circuit readouts of atoms in the ground state, but you can also do a mid-circuit reset, which means in the middle of your quantum circuit, you can decide to cool and reinitialize your ancilla qubits, for example, which is something that you might want to do. And they see that they can preserve coherence when they do this. They can do something similar also if you want to do mid-circuit readout the metastable state instead of the ground state. So this works for both of your two different types of qubits. And sorry, is this part clear about how you use this different electronic structure of the alkaline earth atoms to do mid-circuit readout and operations? Yeah. Sorry, I didn't hear a part of your question. Say that again. So, so there are different ways of imaging. So here it's a little bit different, but the idea. So here we're not really going into the Rydberg state ever in this demonstration. So here you're only staying in this subset of states. But when you do imaging, you typically excite one of the two atoms away, and you only image one of your two qubit states. Yeah. So you excite them to some other state. Okay. Is that correct, Adam? I hope so. Okay. Yeah. So even for the, sorry, maybe I should have commented this before also for the alkali atoms. When you use the hyperfine qubit, now when you do imaging, what you do is you promote one of the two qubit states to some other state that is not resonant with the imaging light, so that you only see one of the two. So you still image one of the two states as losses when you do the image. Okay, so here I wanna, sorry, these slides are a little bit messy, but another application, another thing you can do with these alkaline earth atoms that is really in the spirit of this mid-circuit operation is this so-called mid-circuit erasure conversion. So this is an experiment from Jeff Thompson's group in Princeton. So what he did here, again, he also has ytterbium-171. And here, again, he's using this metastable state qubit where you have these 0 and 1 states. In this case, well, okay, these are details. I'm not going to comment on this. What he did here was to implement two different types of imaging. Because when you do mid-circuit readouts, one of the challenges is you want to do the readouts on fast timescales, which is not always the case when in the types of imagings that I showed you so far. So what you did here was to implement two different types of imaging. The typical imaging is low and quasi non-destructive, so it has high fidelities, but is fairly slow. I think it happens on about 20 milliseconds. And the first one instead is fast, but it's completely destructive. So when you image the atoms, you lose everything. And this happens at two different wavelengths. But the way you use this is very interesting. So the idea is, what it's doing here is it's performing single qubit gates. And in between the single qubit gates, he does this mid-circuit erasure conversion, which means you have your atoms in the metastable qubit here. And the main source of error is that your atoms can decay to the ground state. Okay, so they go out of your qubit subspace. So what he does is, after, let's say, 50 single qubit gates, he images the atoms in the ground state to see if anything has decayed to the ground state. And he keeps the image, then he does another sequence of 50 gates, then he images again in the ground state, another sequence of 50 gates, then he images again, and then he looks at the final result. And then what you see here is that the fidelity of your circuit, when you correct for the measurements, for these mid-circuit measurements, can be increased by a significant amount. So the idea is you detect the atoms that have decayed into the ground state, you convert these into so-called erasure errors, and these erasure errors are easier to handle for quantum error correction applications. And so it's a way of reducing the errors that happen in the system to easier to handle types of errors. So, okay, so this is the second type of application. I also want to mention, I wanted to talk about all these things, then I realized it was not super realistic, but there are other interesting experiments that have been done, again, using alkaline earth atoms. This first one is from Jake Covey's group at University of Illinois, Urbana-Champaign. This is from Atom Computing, a startup that uses this type of tweezer arrays with ytterbium. And this other one is not exactly related to this mid-circuit readout, but it's also an interesting application of this erasure conversion idea that is from Manuel Andrews' group at Caltech. So I'll try to add a few things in the slides before putting them on the website, but these are also very cool things that are happening using this type of alkaline earth atoms. So finally, I wanted to show you the other type of atom array, which is the one that uses two different atomic species. So what is interesting here is that when you have two different types of atoms, you have selective control of the two atoms because the wavelengths of their control lasers are at different, are different. And so when you address one of the two atoms, the other one is not affected. And so the applications that have been recently demonstrated for this in this recent paper, again, from I think a couple months ago as well, is the first one is how you can also do mid-circuit readout of what they call spectator qubits that are basically ancilla qubits, but they give them another name. So here what they did was you have your data qubits and your so-called spectator qubits, and you want to see if the data qubits are affected when you do imaging on the spectator qubits. And basically here what they're plotting is the coherence of the data qubits with or without the mid-circuit readout on the ancillas. And you see that it's basically unperturbed. So you don't see a strong effect of the mid-circuit readout on the ancillas. So then they use this also to do actual mid-circuit correction. So what they do in this case is they use the ancilla qubits to detect noise that happens in the system, and then they use those measurements to feedback on the atoms. And so here what happens is that they introduce on purpose some source of noise. So here they're modulating a magnetic field to introduce noise in the system. They have their data qubits that live their lives unperturbed, so actually perturbed by this, but the ancilla qubits are measured to detect the effect of this of this source of noise, and then they use the information from this Midcircuit readout to feed back on the measurement that they did on the data qubits. And basically what you see is when you don't apply the feed forward, basically you don't see any feature in your data qubit. You're expecting to see oscillation, but when you turn on the feed, instead you recover the coherence of your data qubits. So in this case, they do Midcircuit readout, but they also show how you can apply this to recover some coherence for a specific source of noise in your system. And finally, something very interesting that they did there. And so, yeah, sorry. Yes, which goes to this final point. So the third thing that they did here was, so as we were saying, you would like to be able to reload these atoms that you're using, because when you do imaging, it's destructive. And so again, the fact that you have these two atomic species is interesting, because while you can reload atoms in the ancilla qubit, while the data qubits maintain coherence. And so this is what they showed here. So basically you have your data qubit in some superposition state that you initialize them in. And in the meantime, on the spectator qubits, you reload the MOT. Remember this magneto-optical cloud. So you create this cold cloud of atoms next to them. And they see that, so, okay, here, yeah. So basically this line here shows the coherence of the data qubits in the absence of this more reloading, whereas the blue data show you what happens when you're reloading the MOT. So there is a little bit of a change, but this is already pretty good as a first demonstration. And the two images are simply two different ways of reloading atoms in the tweezers. So this is, as far as I know, the first demonstration of how to do this reloading of your atoms while you maintain coherence in your system. And maybe to comment more about this, this is something that is really crucial to these types of experiments, because as we said, first off, when you do this destructive imaging, you are losing the atoms. But even if you weren't, your atoms have some finite lifetime in your vacuum chamber, and so you're going to lose them sooner or later. And so having the possibility of reloading them from a reservoir is actually very important, especially if you want to be able to scale up to large numbers. And so this is something that the community in general is really working on, and there are a few ideas on how to do that. Yeah. So the important thing here is, so when you do this MOT, you're shining resonant light to be able to cool the atoms, right? Near resonant light. So it's important that the wavelength that is resonant for the spectator qubit is far off resonance for the data qubit. So that light doesn't affect your data qubit because it's not on resonance. So if you had the same type of qubit, that wouldn't be the case. If it was the same atom, that wouldn't be the case. Actually, on a related note, with that kind of atoms, you can probably do something very similar, where you shelve your atom. Actually, what Adam demonstrated is already very close. When he did the Midcircuit reset, he was shining resonant light on the qubits in the ground state, but the qubits in the metastable states were not affected. So this shows you that you can probably do something very similar with this continuous reloading for those kinds of atoms as well. A way of understanding these kind of atoms is that you effectively have two species in the same one, because you have these two different qubits that they're well isolated. And so if you do these shelving operations, you can really do something very similar to what you have here. For these ones, yes. For the alkaline earth, no, they're the same. I saw another question. Okay, this was actually my last slide, so I think we're good. Maybe, we started these lectures discussing, what were the requirements that you would have wanted this platform to have. So maybe I just wanted to give some time for discussion, now that you've seen some of the features that this platform has and some of the applications that have been done. I lost that list because my notes were canceled when I saved my PowerPoint, but I think I can recover it from the videos, but I didn't. But maybe if you have any questions or opinions on what this platform has to offer, what are the challenges that you see going ahead and trying to make this into even more useful quantum computer, I would be interesting to hear them. Or if you have any other questions, or otherwise, I'm done. Thank you. So the reload time here, I believe, is around 100 milliseconds for both of these schemes. I think one is 150, the other one is 90 or something like that. And again, with these alkyl earth atoms in the hyperfine qubit, you have these T2 times that are several seconds. So, well, at least 1 second. So it's still, it's still much shorter, but not super. Anything else? Yeah. Thank you.
I had a question about the video that you were showing.
Mm-hmm.
So I guess my question is, how did you come up with this sequence of like moving the atom?
That's a good question.
Was this like the thing that would be good, or like in terms of, I'm just thinking in terms of like optimality, like
yeah.
There seems to be like a lot of flexibility, like you have both sets maybe moving. I don't know in terms of the challenges of getting.
Yeah, no, this is a very good question. So here we optimize this manually. So what you're trying to do is minimize the number of gates and minimize the number of moves. And also you have some technical constraints. As you see here, we're always moving the atoms in these rectangular grids because basically you cannot have atoms crossing each other. If you remember how these acousto-optical deflectors work, you cannot do that operation. So you have some constraints, but we're actually thinking a lot about this, and we're collaborating with a group that is basically using machine learning and artificial intelligence to optimize this, because for this it was already, well, it was not super challenging to optimize this, but we did a few versions and we thought hard about what was the best configuration. But if you think of scaling this, it becomes hard very quickly. And so we need to find a way to find the optimal solution for this sequence of operations in a general case with larger number of qubits. And I think doing that manually starts to become very hard.
Yeah, and the general circuits too.
Yeah.
Trying to do like one thing with scale.
Yeah, no, exactly. It's actually a very good point. And also you have some kind of limitations that come from the experiment, and so you need to take them into account. But yeah, that's actually a thing that we're working on how to create an algorithm that optimizes this for us. Yeah. Mm-hmm. 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 Well, maybe together. Yeah. Okay. Yes. $24, I think. Yeah.
What is the most important part of the capability or developing?
I mean, I think the single qubit operations are good. The 2 qubit operations are getting there. I mean, this 99.5 is, and I put some references in the slides. That is the one result from Harvard, but there are other results from other groups that are getting very close. So I think there we can already start doing some logical algorithms with that kind of fidelities, because you reach the threshold for some of these codes, and so you can start to say, okay, let's put many atoms together, let's build different logical qubits, have them do gates and blah blah. I think for the community, it's a parallel effort. I mean, on one side, you're trying to optimize these gates, but I think at this point, it's not much about developing new protocols. It's more about, I think this protocol that we're using now for the CZ gate is pretty optimal. I mean, there might be better, but for now it works very well. You want to reduce these sources of incoherence in your experiment. So you're trying to get higher powers. You want to minimize some sources of errors that you can have from your lasers. So there are these technical challenges. Some of them are easier to solve, some of them are harder. So for example, having more power in your lasers, it's not completely up to us. Sometimes we need to push companies to develop those lasers for us. So I think these are parallel efforts. So we're trying to do that while we also start using this to do something useful. And so there are people that are using this and trying to apply it to do, again, some kind of logical algorithm that is interesting and that starts to demonstrate the building blocks of actual error correction. I would say more, maybe to me is an outstanding question is still, what is the kind of algorithms that we want to do here? Like now that we start to have the capabilities, what are the things that we really want to do? I don't think it's the surface code. So what is it? What is the thing that we should try to build up to, which is, at least to me, is not super obvious yet. So in these days, we've talked about a lot of different things. Yeah. Yeah, and in a sense, I mean, of course, if you want to have a quantum computer coming out of this, you need to be able to solve all of them, right? So I guess it's a matter of preferences, what you think is more important. I think to me, what's exciting in this platform is that, in the different groups that are working on this now, there have been so many different developments most of the things that I showed you are from the last year. So it's really growing very fast, and different groups focus on different things. And so I think the community as a whole is moving in the right direction with people, concentrating on different aspects of the challenges that we have. But, yeah, I think in a sense, you cannot just, at least in my perspective, if you only focus on one problem, maybe you get very well at that, but then everything else doesn't work in the end. And so you get stuck with 2 qubits that work very well, but you realize that scalability is impossible. And so, then you're stuck with 2 very nice qubits, but that's about it. Yeah.
What about analog qubits?
Mm-hmm. What about it?
Some theories, so you have no CZ gate and the swap gate, correctly. Can you also perform other qubit gates without composing of those gates?
Can you perform? I mean, so far we're doing everything starting from the CZ gate because it's the one that we can do. I guess in principle, yeah, you could think. Oh, actually, I mentioned it in the first slides, and then I didn't really comment on this. There is an extension of this type of CZ gates that you can do with 2 multi-qubit gates. So you can do like Toffoli gates, and by just putting more atoms into the blockade radius, you can do multi-qubit entangling gates. But if you're talking just about 2 qubit gates, different kinds, I don't think anything else has been tried yet on these atoms, but yeah. You mean for quantum simulation applications? Yeah. Yeah, it would be nice. I mean, but okay, for quantum simulation, I have to say, you typically do, the analog type of Hamiltonian-based analog dynamics, and then, you can mix with some layers of digital operations to do some specific, measurements or whatever. But yeah, if you want to do everything in a, you know, a quantum simulation in a digital way, yeah, you need to talk to that. Yeah, yeah, that's correct. I mean, if you have an idea of another gate that we can do, I'm happy to hear. But this is the one that has been developed so far. Yeah. Yeah. What do you mean with fancier? Like what? I mean, yeah. So I think something interesting about this type of dynamical connectivity is that you can do things effectively in 3D. So going back to the hypergraph states that you were mentioning, yeah. I mean, okay. The Harvard group that I'm no longer part of is working on some different types of. I don't want to spoil much, but you're gonna see something. Hopefully on the archive fairly soon. So, you know, we are starting to implement this, to use this to implement different types of graphs. As I was mentioning, I think we're still struggling to find what are the most interesting ones that we want to do. So if you have ideas, again, happy to hear. But yeah, I mean, yeah, this was just the first of hopefully many. Anything else? Okay. Otherwise, good. Good. Thank you.